Curves in industrial design, polynomial parameterizations of curves. Any point on a line segment with endpoints A and B can be written as a barycentric combination of A and B. If we write the coefficients alpha and beta in the form 1 minus t and t, then all the points on the line segment from A to B can be described as 1 minus ta plus tb as t runs from 0 to 1. Written in this way, the line segment from A to B is said to have a polynomial parameterization of degree 1. This is because it's expressed in terms of linear functions of t. Linear functions are polynomials of degree 1. If the points A and B have coordinates a sub 1 and a sub 2 and b sub 1, b sub 2, then when we write the combination 1 minus ta plus tb in terms of the coordinates of A and B, we obtain a point parameterized by t. The x-coordinate is a combination of the x-coordinates of A and B, and the y-coordinate is a combination of the y-coordinates of A and B. For example, if A is the point 2, 4 in the plane and B is the point 6, 2 in the plane, the line segment that runs from A to B can be parameterized as 2 times 1 minus t plus 6t as the x-coordinate, 4 times 1 minus t plus 2t as the y-coordinate. What we want to observe here is that both the x-coordinate and the y-coordinate are functions of t, and they're linear functions of t. A particular value of t in the unit interval determines a particular point on the segment. For example, the midpoint of the segment, here indicated in red, corresponds to the value t equal to 1/2. Substituting t equals 1/2 into our expression s of t for the point on the segment, we obtain the point 4, 3. We can check directly that this is the midpoint of the segment between 2, 4 and 6, 2 by summing the coordinates and dividing by 2. 2 plus 6 divided by 2 gives us 4, and 4 plus 2 divided by 2 gives us 3. Here we see again the parameterization of a line segment. As we change the value of t, the point P corresponding to that value of t changes as well. What we want to emphasize here is that the coordinates of P, x and y, are themselves functions of t. The change as t changes. A parameterization of a curve is a mathematical description of how a point moves along the curve. It depends on a single variable, usually called the parameter, and usually denoted by t, because one is thinking of time. T abbreviates time. In general, there are many ways of parameterizing a given curve. A parameterization of a planar curve has the form c of t equals x of t, y of t, where x and y are functions of t that describe the change of the x and y coordinates of the point as functions of t. A spatial curve has a parameterization of exactly the same form, except it has a third coordinate, which we denote z of t. It describes the motion in the third direction. A parameterized curve is said to be polynomially parameterized if its coordinate functions are polynomial functions of the parameter t. In this case, the largest of the degrees of the coordinate polynomials is the degree of the curve. For example, the curve c of t, whose x-coordinate is 1 minus 2t plus 3t squared and y-coordinate is t plus 2t squared minus t cubed, is a planar polynomially parameterized curve of degree 3. Its x-coordinate is a quadratic polynomial of t, and its y-coordinate is a cubic polynomial of t. We can write the same curve in a different way, as a combination of points. In this case, 1, 0, minus 2, 1, 3, 2, 0, minus 1, coefficients 1, t squared, and t cubed. The relationship between this expression and the first expression is the following. For instance, the point a1, that's the coefficient of t, comprises the coefficients of t appearing in the functions which describe the coordinates x and y of the point on the curve. So for instance, the x-coordinate of t, the coefficient of t is minus 2, and then the y-coordinate of t, the coefficient of t is 1. This yields the point a1, minus 2, 1. The point a2, 3, 2, corresponds to the coefficients of t squared in the parameterization of the curve. The coefficient of t squared in the x-coordinate is 3, and the coefficient of t squared in the y-coordinate is 2. Here we see a parameterization of a curve. And as we change t, values of the functions of its x, y coordinates change, and the point moves along the curve. Each value of t corresponds to a different point on the curve. Here we see that if we change the values of t, we trace out an arc of the curve. That arc is indicated in red. We can also choose a different parameterization of the curve. The points on the curve P and Q correspond to the same value of t, but in different parameterizations. As we move t along the curve, they both move along the curve, but in different ways. We can see that for different values of t, the separation between P and Q changes. First, they're very close together. They separate quite rapidly, P moving much faster than Q. Then Q starts catching up with P. And at the end again, they coincide. A parabola can be described as a polynomial curve of degree 2. Given 3 points, A0, A1, and A2, we consider the curve, which is the combination of A0, A1, and A2 with coefficients 1, t, and t squared. It's an arc of a parabola. If we choose the points in the plane, we get a parabola in the plane. If we choose the points in the space, we get a parabola in space. However, it's worth noting that a parabola in space always lies on a plane. Precisely, it lies on the plane that contains the parabola's focus and its directrix. Here we see a parabola in space. As we change our point of view, we can see that this parabola lies on a plane. This is the plane indicated in light blue. When we look exactly along the plane, we see the parabola as a line. And we change our perspective, we can see the parabola again. A cubic polynomial curve, or cubic curve for short, is a polynomial curve of degree 3. To specify such a curve, we have to pick 4 points, A0, A1, A2, and A3, which we express as a combination of coefficients 1, t, t squared, and t cubed. The result is a cubic polynomial curve. Again, we can choose these points to be in the plane or in space. However, in the case that we choose them in space, the resulting curve need not lie on a plane. In general, it will not. Here we see a cubic curve passing through the points A, B, C, and D in the plane. As we change the value of the parameter t, point P moves along the curve. Here we see a cubic curve in space. We see that no matter how we look at it, it does not lie on a plane.